Hello. This video summarizes a paper that looks at improving the usability of self-adaptive systems where a human user is involved in the decision making. The main issues are providing transparency and control to the user in a natural and intuitive way. The approach taken is to create a digital twin of the managed system and allow the user to interact with it using a virtual reality interface. To evaluate, 14 participants complete a simple task using both procedural and declarative control schemes and provide feedback. The paper title is Enhancing Human-in-the-Loop Adaptive Systems Through Digital Twins and VR Interfaces, and it was authored by Enes, Kadiray, Ivan, and Gregor, all from the Paderborn University in Germany. It was presented at the 16th International Symposium on Software Engineering for Adaptive and Self-Managing Systems, also known as SEAMS, which was held from 18 to 21 May 2021, and it was done virtually, but it was originally going to be in Madrid. So, in self-adaptive systems, we often want no human in the loop, but there are some areas where it can be advantageous or even required. And these are especially in applications that need to deal with new situations that couldn't be anticipated before in the design time of the system. And one example can be autonomous robots in disaster recovery scenarios, or possibly a assembly robot that keeps having to assemble new things. So in order to solve these problems, you can add a human into the loop, in the MAPE-K loop, that is. So in a lot of situations, the monitor, knowledge, and execute parts of the MAPE-K loop are done by the system, and the analyzing and planning are done in part by humans. This, of course, poses a few challenges, and the main ones are transparency, controllability, and user satisfaction. So, the transparency. The human obviously needs to know about the system state and what's going on internally. For simpler systems, it's a lot easier, like a simple thermostat. You can just, you can display the temperature and you can set a temperature that it should achieve, and that's quite easy to understand and design an interface for. But once you start needing to tell robots what to do, it gets a lot more complicated. And in those sort of complicated systems, it's also important to understand why decisions are made. And then once you can understand the state of the system and what's going on, you also need to be able to control the system. So in that case, the human needs to be able to issue the commands to the system, and that's not always simple. And obviously, usability and user satisfaction are pretty big in this, and if they're bad, then the system might not perform very well and could just do poorly in its tasks. So this paper looks at a fair bit of related work. So first, it justified the need for a human in the loop. So one of the things that they remarked was that it allows users to trust the system if they are in the loop, and that there's also a lot of different ways that humans can be added into the MAPE-K loop. The one main area of that this can be done in is the human-robot interaction area, and there's sort of a scale of how involved a human is, and it's sort of between teleoperation at one end, so the human having full control of the system, or the robot in this case, and autonomy, where the human is just providing goals and the robot figures the rest out. And this identified a lot of challenges the literature did. Literature also mentions that digital twins have been used before, but not in the way that this paper does it. So, the main idea of this paper is to basically build a system and evaluate it. So the system consists of a physical part, which in this case is a physical doobot magician with a suction cup, which is just a robot arm with a suction cup, and it has some cubes, as we'll see later on. So the digital twin is the user interacts with the digital twin via the virtual reality interface, and the system passes sensor data between the robot OS that is controlling the DoBot magician and the Kinect camera, and it is able to make a 3D environment for the user to interact with. And as you can see in the diagram, the monitor, execute, and knowledge stages are done by the system, and analyze and plan are done by the human in part. So the two main control strategies are procedural and declarative, and we'll see more about those in the next slides. So this paper is better than the previous approaches because it compares the direct control, which is the procedural, and being able to direct control the robot, that is, and specifying the desired state, which is the declarative. So in direct control, or procedural, the user controls the digital twin of the DoBot magician, and then it basically records all the actions like a macro, which can then be played on the real robot. And the user can do this as long as they want, and then they execute it. And the declarative option is basically set the goal state by arranging the blocks in the virtual reality, and then tell the robot to figure it out using its AI planner. And the advantage of this as well is that unforeseen scenarios can be handled, because humans are generally quite good at that, at least better than machines. So this is the virtual reality interface, both for procedural and declarative control. It's changed by those two tabs at the top. So this is what you would see if you had the virtual reality headset on. And this is what the robot physically looks like. And this also shows for the evaluation example, for the evaluation task, what they need to do, which is basically put the blocks in the spaces in the desired order, which is red, green, and yellow. So the evaluation, they evaluated it with 14 participants, and they basically had a bit of brief training with a video and that. Then they performed the task I just mentioned, which was moving those blocks. And then they answered some questions in the form of a system usability scale survey and a presence questionnaire and a general interview. They measured the efficiency and effectiveness, which is basically the time taken and how many of the blocks ended up in the right position. And yeah, the questionnaire. And basically the procedural on average took 172.55, and the declarative took 111. So that shows that the declarative is a little bit quicker, because it is quite manual and laborious to tell the robot each exact action it has to make. It's fine for a simple task, but if you're doing it every day, it wouldn't be much fun. So the effectiveness in the VR was almost 100%. One user, 92.86, but one user failed to hit record on their thing, so their run was basically 0. So other than that, everybody got it correct in the VR. But the real world was 73 with procedural and 80.95 with declarative. And they sort of mentioned that might be because when the robot is planning it, it tends to get the suction cup centered better than when it was doing procedurally. So the presence questionnaire was 73 for both, and the system usability score was 63 for procedural and 80 for 54 for declarative. So most people did like declarative better. So some small critiques. There was only a small number of testers, and they're all computer science students, so not always representative. And it was also the first time these people used the system, so not much more time to get experienced, and the task was quite simple.